Welcome back to chapter 25. We have done our video on mirrors, and now we're going to work on our video on lenses. So you can see we're on section 4, thin lenses. So the observer is always on the positive side of the lens. We remember that from previous examples when we've talked about the mirrors, that you as the observer define the positive side. So with a converging lens, light from a distance enters the lens and then gets focused at a place on the horizontal axis called the focal point. Converging lenses are convex. Remember that convex means it bulges out. They'll always have a positive focal length. The object distance by definition is positive. It allows us to use a single equation. And the image distance is going to vary. It'll be different depending on where the image ends up being focused. So our rules for these diagrams are very similar to the rules for converging mirrors. That is, that any light that comes in parallel to the horizontal axis will exit through the focal point, and any light that comes in through the focal point will go out parallel. I know we don't have that written down. Maybe I should have. Maybe we'll do this. Oh, no, I remember now why I didn't want to do that. My apologies. I was thinking ahead and I was thinking incorrectly. We don't want to say that. So in parallel out through the focal point. And then now this is, the second rule is different. It's in through the center of the lens, out straight through. In through the center of the lens, not the center of curvature, but the physical center of the lens. Out straight through as if unrefracted, as if not bent at all. We have a series, oops, I overshot. I'm bad to do that. We have a diagram. So the red ray is parallel to the central axis. So in parallel, and it should stop at the center of the lens. I think it's really hard to tell on this drawing because the lens is so thin that it ought to stop in the middle. So in parallel out through the focal point. The blue one is the second ray we talked about, in through the center of the lens, straight through. The reason I don't want you to draw the green one, you can see I've borrowed this image. Let's don't do the green line. It confuses people. So in parallel, out through the focal point, in through the center, straight through. You as the observer are over here on the right-hand side. So you see the blue and the red ray and your mind traces them back to the point of intersection, and that's where the top of the image will end up being. So in this case, our image is inverted. It's upside down compared to our object. It is reduced. That means it's smaller than the object. And it's a real image. If we put a viewing screen right here, we would focus that light on it and be able to see the image. So the two rules: in parallel, out through the focal point, and in through the center, straight through. We're going to draw these diagrams in class. So again, in parallel, out through the focal point, in through the center, straight through, and where the two cross each other is the point of intersection. And then again, in parallel, out through the focal point, in through the center, straight through. This second diagram is not going to have a point of intersection over here on the real side, so you'll have to extend the two rays back as a dashed line. And again, we'll do these drawings in class, and you'll have another opportunity to practice in lab. So what do we use converging lenses for? Well, we use them in eyeglasses. And we also use them to magnify things. A magnifying lens or a magnifying glass is a converging lens, and you just have to be really close to it. It's one where the object is inside the focal distance, so it's really close to the lens. Our second type of lens is a diverging lens. I'm doing it again, aren't I? Diverging lenses. So diverging lenses are concave. They sink in. They have a negative focal length. So diverging lenses are similar to diverging mirrors, except obviously the shape is different. And a diverging lens, they're concave. They always have a negative focal length, and they always make erect, reduced, and virtual images, just like diverging mirrors always make erect, reduced, and virtual images. So the rules for these ray diagrams: in parallel, out as if coming from the focal point, and then in through the center of the lens, out straight through. This rule holds for any kind of a lens, a converging lens or a diverging lens. The second rule is the same. All right, so let's look at our little sketch. So the red ray is in parallel and then out as if from the focal point. So the focal point is over here for a diverging lens. You, the observer, are on the right-hand side. The object is on the left. So in parallel, readjust your ruler as if it's connecting with the focal point, and it comes out. Remember, solid on the real side, dashed on the back side. And then the second rule was in through the center. So that's the physical center of the lens, in through the center, straight through. You as the observer will see this red ray and this blue ray. Your mind will trace them back in a straight line until it finds a point of intersection, which is right here. And so that's where your mind will tell you the top of the image is located. So this little green arrow represents the top of our image. Our image is erect, our image is virtual, and our image is reduced. So the image is erect, virtual, and reduced. And that's the only kind of image a diverging lens can make. It doesn't matter where you put the object. You could put it close, you could put it far away. You're still going to see an erect, reduced, virtual image. And we have drawings, and we'll do those in class. And again, you'll have opportunities in lab to pursue this. So where do we use these diverging lenses? Well, primarily in eyeglasses, but there are certainly other places they can be used. So an optometrist uses, I'm just going all over the place today, aren't I? So an optometrist and ophthalmologist, when they write your prescription for your eyeglasses, they'll talk about the power of the lens. Power is defined as 1 over the focal length. Power is defined as 1 divided by the focal length, where your focal length is measured in meters. Power is measured in diopters. So 1 diopter is equal to 1 meter to the minus 1. So if you had a focal length of 2 meters, 1 divided by 2 would be 0.5. So your power would be 0.5 diopters. If your focal length is 2 meters, the power would be 0.5 diopters. All right, some lens problems. These are really very similar to the mirror problems. You have to summarize things the same sort of way. So we have an object 30 centimeters in front of a lens image, and the image is 10 centimeters in front. What type of lens is it, and what's its focal length, and is the image erect or inverted? So we know that the object distance is 30 centimeters. By definition, even though in front of the lens is not on your side, by definition, all object distances for us will be represented as positive numbers, so 30 centimeters. So for the image, we've said the image is 10 centimeters in front of the lens. So for an image, in front of the lens means it's negative. So the image distance is negative 10 centimeters. They want us we need to find the focal length so that we can decide, is it a concave or convex lens? And And we'll need the magnification to decide if it's erect or inverted. So we have our three formulas. 1 over F is 1 over DO plus 1 over DI. Magnification is minus DI over DO is HI over HO. And F is equal to R divided by 2. Same three formulas as our previous information about mirrors. We have DO and DI, we can find F. So 1 over F is 1 over DO plus 1 over DI. So 1 over F will be 1 over 30 centimeters plus 1 over negative 10 centimeters. 1 divided by 30 gives us 0.0333. 1 over 10 is 0.1. So 0.0333 minus 0.1 gives us negative 0.06667. Notice that I kept the units of centimeter. You don't have to convert to meters unless they tell you to. The focal length would be 1 divided by that negative 0.0667. So F is 1 divided by this negative 0.06667, and that gives us a value of negative 15 centimeters. Negative 15 centimeters. So what can we tell if we know that? It is a negative focal length, and that tells us that we have a diverging lens, which is a concave lens. We know that concave lenses have erect, reduced, and virtual images, and that's the only kind of image you can have. So I know it's going to be erect, reduced, and virtual. I want to find the magnification. We want to find the magnification. So M is equal to minus DI over DO. We don't have any heights, so I left that part of the equation off. M is equal to minus DI divided by DO. So it's equal to minus negative 10 centimeters over 30 centimeters. Well, a minus makes it a plus. 10 divided by 30 is 0.333. Remember that magnification does not have units. Because the magnification is less than the number 1, we know our image is reduced. It is shorter than the actual object. It is shorter than the actual object. Because the magnification is positive, we know our image is erect. A positive magnification tells us we have an erect image. So if M is positive, the image is erect. If M is less than 1, the image is reduced. Let's look at a second example. A converging lens has a focal length of 5 centimeters. Object is 1 centimeter in front of the lens. Where is the image and what kind of image is it? So we know that F is 5 centimeters. They told us it was a converging lens, so we know F is positive. The object distance is 1 centimeter, and object distances are always positive. We want to find the image distance and the magnification, and we have the same three formulas we've had before. 1 over F is equal to 1 over DO plus 1 over DI. M, the magnification, is equal to minus DI over DO, which is HI over HO, and F is equal to R divided by 2. So we have F and DO, we can find DI. DI would be from the formula 1 over F is equal to 1 over DO plus 1 over DI. So if we plug in 1 over 5 centimeters equals 1 over 1 centimeter plus 1 over DI. Well, 1 divided by 5 is 0.2. 1 divided by 1 is just 1. We have to solve for 1 over DI, we'd have to subtract 1 centimeter from both sides. So 0.2 minus 1 centimeter will give us 1 over DI, but 0.2 minus 1 is negative 0.8. So DI is 1 divided by negative 0.8, which is negative 1.25. The unit is centimeters because we never changed centimeters to meters, we just left it. Notice that DI is a negative number, and that tells me it's a virtual image. So we can know a lot by knowing just some of these numbers. It's a virtual image because the image distance is negative. If the image distance is positive, we have a real image. So to summarize, our image is virtual because DI is negative, and it's 1.25 centimeters in front of the lens because you stand behind the lens. You as the observer stand behind the lens. Any image on your side will have a positive image distance. Any image on the other side of the lens, in front of the lens, will have a negative value. If you want to find the magnification, M is equal to minus DI over DO. So M is equal to minus negative 1.25 centimeters divided by 1 centimeter, which gives us a positive 1.25. What does that tell me? Well, positive 1.25 is bigger than 1. So I know it's enlarged, not very much, but it's enlarged. And because it's a positive number, I know it's erect. So the image is erect because M is positive, and it's enlarged because M is greater than the number 1. And we're going to stop our video here. It's an easy way to stop, and then we'll pick up with the video 3 with the index of refraction.